Welcome. In this video lecture, I am going to talk about the multivariate regression model using R. First of all, we will discuss what is a multiple linear regression model, how we can estimate the parameters of the multiple linear regression model using the method of least square, and then I will discuss about the model fit, means how good the particular model is and whether this goodness of model is significant or not with the help of ANOVA test. Then we will talk about by fitting the multiple linear regression models like model 1, 2, 3, 4, and out of that which model is the best model we can use to predict our response variable. We also talk about the standardized version of the parameters. So here we will estimate the parameters and then we will also talk about their standardized version of the parameters, okay, which we will going to estimate through R, and then we will see how we can interpret those standardized parameters of estimates. And then we will check the accuracy of the regression model. First of all, we will see whether is there any particular case, or you can say the data point, which is basically disturbing the regression model. Okay, if there is, then we will try to delete that case or the data point, and after deleting it, then we will fit the regression model. Okay, so once we have cleared this point, then we have to assess the number of properties. Number one, the errors must be independent, okay, through the Durbin-Watson test. Then we will check the multicollinearity between the independent variables. If there is the multicollinearity, then model is not good. So we have to make sure that there should be no multicollinearity. So with the help of VIF, which is called as variance inflation factor, okay, and then we will check the normality of the residue as well as the homogeneity of the variance. So let me first of all start with what is the multiple linear regression model look like. So here we have a multiple linear regression model in which we have one dependent variable and we have multiple independent variables. And remember that whether we are talking about the simple linear regression model, whether we are talking about the multiple linear regression model, your dependent variable must be the quantitative variable or a numerical variable. It should be measurable form in an interval scale or a ratio scale. Whereas your independent variables must be also the quantitative variable, but it also could be in a attribute form. Okay, how we are going to deal those attribute type of variable we will discuss later. But first of all, let's assume that your independent variables also the quantitative variables. Okay, and our objective in the regression model is we want to minimize this random error. Okay, so we want to minimize this random error by using the method of least square approach. Okay, how we can do that we will discuss later. So remember that this is y-intercept, these beta 1, beta 2, beta k are the population slope. This is your random error, and once we have estimated those parameters, we can represent with beta naught, b1, b2 up to bk, or we can represent with beta naught as an estimated value, beta 1 as an estimated value, and so on. Okay, now the question is how we can do this. So we want to estimate the parameters of beta naught, beta 1, beta 2 up to beta k. So first of all, let's discuss that how the regression model look like, how the data look like in the multiple linear regression model. So we have y, that is a dependent variable, we have k independent variables. Okay, the dependent variables values are the measurable values, as well as the independent variables are the measurable values, or we can say these all are the column vectors. Okay, so we can represent this one is with the help of summation j1 to k bj xij plus error epsilon I. Okay, so where I is representing basically the equation number, j is representing in a particular equation the variable, or you can say j is basically representing the particular variable or a column, I is basically representing the row. Okay, so that is basically the observation perspective. Okay, Now the ultimate target is we want to minimize this one. So first of all, how we can calculate the epsilon? That is the actual value minus the predicted value. Okay, so this is the epsilon, or you can say residual or error. So we want to minimize the sum of square of error. Okay, so by putting y hat in place of y hat, we can put the value of this one, that is equal to this one. Okay, now if I am going to differentiate with respect to beta naught and put it equal to 0 and try to find out the value of beta naught, that is basically, if I am just simplifying this one, this would be equal to this equation. Now if I am going to differentiate with respect to beta 1, I am going to get this equation by placing it equal to 0. And then if I am going to differentiate with respect to beta 2, then I am going to get the third equation. Then if I'm going to differentiate with respect to beta k, I will get the last equation. Now, if we simultaneously solve these equations, we would be able to get the values of beta naught, beta 1, beta 2 up to beta k. So the similar thing we can calculate with the help of matrices. Okay, how we can do that? Okay, the same equation we can write down this way. So where is y is a column vector, x is basically n by m matrix. Okay, and b naught is a column vector, and similarly epsilon are the column vector, right? Okay, so now basically these ones are basically represented with beta naught value. Okay, so these are basically the constant number, whereas x1 is representing this one, x2 up to xk. Now, in order to find out the values of the beta naught, beta 1 up to beta k, we can represent the normal equations which we have shown over here. So these are called as the normal equations. So how we can represent that those equations in the form of matrices like this way? That means x transpose into x. So if I take the transpose of this matrix and multiply itself, I will get this value, and then is equal to x transpose into y. So I will get this one. Okay, so by multiplying x transpose into x, I will get this matrix. Then this is basically beta's value, that is basically this one, we want to estimate this one, and this is basically equal to this one. Now, in order to calculate the value of betas, okay, what we need to do is we will try to find out the x transpose x inverse. Okay, because it is going to be divided by this one, and then x transpose y. Okay, so that would be the formula to find out the values of beta naught, beta 1 up to beta k. But obviously we are not going to discuss how we can do that manually, so we are going to discuss how we can estimate the values of these betas with the help of R. So for that, I'm going to use the data set of album sales. So where the dependent variable is sales, where are the independent variables are the advertisement expenditure. So we have the airplay and we have the attractiveness. So this is the amount we are spending in thousands basically. Okay, in the advertisement expenditure in thousands of pounds, right? Whereas airplay is basically the number of times the song from the album are played on a radio during the week. Similarly, attractiveness is basically the attractiveness of the band, which is basically from 0 to 10. We have scaled it up, and the 10 is basically indicating the more attractive that particular song is. Okay, so now let's fit the regression model using R. So how we can do that? So let me open the R code. Okay. So here we have the code for the to assess the data set. Okay. So I'm saying that read.dlme, basically we have the data in DAT format. Okay. You can say in the text format. Okay. So header is equal to true mean the first row would be considered as the name of the variables. So if I run this one, because we have the data set in the same folder in which we have created the project. Okay, so if I am going to run this one, okay, right now it is assessing it. Okay, as you can see that right now we have this data set we are reading it. So in order to view this data set, we have a command capital V I E view. Then we can use album2. Okay, and then if I'm going to run this command, we can see this data set. Okay. Now, in order to find out the regression model, so first of all, what I am going to do is I'm going to fit only a simple linear regression model where we have a dependent variable sales, where independent variable are the advertisement expenditure. Okay, that is this one. So with the help of lm sales tilde sign, that is this is the dependent variable, this is independent variable, this is the tilde sign. Okay, and then data is equal to the name of the variable in which we have stored the data set. So now if I run this command, so after running this command, so what R will do, it will run the simple linear regression model and save the result in this particular variable. So in order to see the result, we have to run this command summary and then in the name of the variable in which we have stored the results of the linear regression model. So as you can see that this is the value of beta naught, this is the value of beta 1. With the help of t-test, we can check that whether the results of these betas are significant or not, because both the p values are less than 0.01 even, so it is highly significant. So we can say that advertisement expenditure is significantly affecting the sales dependent variable. Okay, or we can say that with the help of R square, that 33% of the variation in the sales is due to the advertisement expenditure, right? That is basically I am talking about this one, as well as the parameter estimation. So let me show you through with the help of even this one. Okay, uh, that is basically this one. So we have run the first model. Okay, let me run the second model first and then I will show you the result. So the second model we have fitted, that is we have the dependent variable sales and then we have three independent variables. We have advertisement plus we have airplay, we have attractiveness, and the data is equal to album 2, and we are going to store this result in the variable album sales dot 3, and then we are going to see the results. Okay, now we have the results of album sale 2 as well as album sales 3. Okay, so now let me show you the two models result. Okay, first of all, we have model 1 when we have one dependent variable and one independent variable. Model 2, again, obviously, we have one dependent variable and we have three independent variables. So let's first discuss regarding the model fit, whether how much variation in the sales variable this independent variable is able to explain. Similarly, how much variation in the dependent variable these variables is able to explain. So with the help of R square, we can say that 33.45% of the variation in the sale is due to the advertisement budget, or we can say that 33.46% of the variation advertisement budget expenditure is able to explain in the sales variable. Okay, whereas in model 2 we can see that the R square value is 66.47%. So that means the advertisement budget, airplay, attractiveness is able to explain 66.5% of the variation in the album sale. Okay. Now we want to test whether these models are significant or not, mean significantly good fit models or not. We will check model 1 as well as model 2. Right now we are not talking about which one is the better one. We are just checking whether the model 1 is significant, which means whether attractive advertisement expenditure is significantly able to explain the variation in the sale. Similarly over here, whether advertisement expenditure, airplay, attractiveness is significantly able to explain the variation in the sales. So how we can do that? We can do that with the help of ANOVA test, where H naught is look like this one. This is basically the H1. Okay, where at least one of the beta j's is not equal to 0. Okay, and this is basically the formula, but in R we are getting these results. As you can see that model 1 as well as model 2, both the models F test statistics against that the p-value is less than 5%. Okay, so we will say that these models are significantly fit model or a good model in order to explain the effect on the sales of these independent variables, whether we are talking about the model 1 or whether we are talking about the model 2. But now the question is which one is the better one? Okay, whether model 1 is better, whether the model 2 is better. So for that we again apply another F test statistics, okay, which would be able to tell us whether the model 1 is the good fit for this particular data set or whether the model 2 is good fit. So this is known as the model comparison in hierarchical regression. Why we are saying hierarchical regression? Because first we develop a linear regression model only with one independent variable, and then we have developed with the help of three independent variables. So you can incorporate if you have more variable, like model 3 we have developed with the help of two variable or a four variable if we have. Okay, so now I want to check whether the model 1 is the better one or whether the model 2 is the better one. Okay, as you can know that model 1 is basically we have the dependent variable and only one independent variable, whereas the model 2 we have the dependent variable and three independent variables. Okay, and in R basically we have a function called ANOVA. In this particular variable we have basically fitted this model. In this particular variable we have fitted result of having this model, and once we get this result, so with the help of this p-value we can easily say that because it is less than even 1%, we will reject h naught. Reject h naught mean model 2 is significantly better than the model 1. Okay, basically what R is going to do is it is going to compare the R square of the two models, and it will say that whether in model 2 R square is significantly improved compared to model 1 or not. So as we have seen that because the p-value is less than 1%, so we can say that model 2 is significantly better fit compared to the model 1. Okay, now let's discuss about the parameters estimation. Okay, so first of all, uh, once we have run this model 2, that is basically sales and advertisement expenditure, airplay and attractiveness, we got the parameter estimation. This is the value of beta naught. Okay, this is the value of beta 1, beta 2 and beta 3, right? Because we have the budget in thousands pounds perspective. Like right now we can say that how we can interpret this advertisement budget expenditure, that basically it is saying that for every 1000 pounds spent on the advertisement expenditure, an extra 0.085 thousand, which means albums are going to be sold, which means 85 albums are going to be sold by spending 1000 pounds on the advertisement budget expenditure. But remember that this would be only true if we are going to assume that the effect of the attractiveness and the airplay effect is going to be constant. Similar interpretation is for airplay, similar interpretation for the attractiveness. Okay. Now, in order to check the significance, so we are going to check the values of the p. Okay, because all the p values are less than 1%, so we can say that the effect of advertisement expenditure as well as airplay as well as the attractiveness is significant on the response variable, which is a sales variable. Okay, so there is another way to check whether these variables are significantly affecting the response variable, okay, or not. So with the help of confidence interval, so we can also check this one. That is because that is right now we are calculating 95% confidence interval. So if you are interested to find out the 99% confidence interval, so what would be the command? That would be conf int album sales to and level is equal to 99. So now it is going to show us the 99% percentage of the confidence interval. Okay, so if the value of 0, which means if I am going to check whether the advertisement variable is significantly affecting the response variable or not, because for that the h naught will be the beta 1 is equal to 0, whereas alternative would be beta 1 is not equal to 0. Similarly, for airplay, h naught will be beta 2 is equal to 0, whereas the alternative is beta 2 is not equal to 0. For attractiveness, h naught would be beta 3 is equal to 0 and alternative would be beta 3 is not equal to 0. If the 0 value is lying within this confidence interval, we will say accept h naught. If 0 value is not lying within this confidence interval, we will say reject h naught, because in none of for these variables the 0 value is lying within these confidence interval. So we can easily say that we should reject h naught in all three cases, which means advertisement expenditure, or you can say advertisement budget, has significant effect on the sales. Similarly, airplay has a significant effect on the sales. Attractiveness has a significant effect on sales, right? Now, once they have the significant effect, we can check from the values of these whether these effects are positive or negative. As we can see that this is a positive effect, this is also positive effect, this is also positive effect. So which means by investing more and more on the advertisement budget or expenditure, we will able to increase the sales. More the song is going to be played on a radio, okay, higher the sale will be for that particular album, and so on. Okay. Now let's calculate the standardized versions of these regression coefficients. So these are basically the normal estimation of the you can say parameter estimation of the regression model. Now we are going to calculate the standardized version of the B's. And what's the difference? Basically, the normal parameter estimate of the regression model are depend on the unit of measurement of the variable, whereas standardized variables are not depending on the unit of measurement. And how we can interpret those one? The number of standard deviation by which the outcome variable will change. As a result, one standard deviation change in the predicted or the independent variable, which means first of all what we are going to do is we are going to calculate the standard deviation of the dependent variable, we are going to calculate the standard deviation of the independent variables. Okay, so once we have, I believe I made some mistake over here, so we have to use the, I believe, album 3, right? I think so. Okay, so depending upon in which variable we have stored the data, whether 2 or 3. Okay, so the name of the variable, let me check. We have, okay, album 2, yes. Okay, so we have stored the data in album 2 variable. Okay, so now we are going to find out the standard deviation of this particular variable. We have find out the standard deviation of this variable. We have find out the standard deviation of this variable. So let's discuss first of all how we can calculate the standardized coefficient of the regression model using R. So for that we have to use this package. Okay, and then we are going to use the function lm.beta and then the name of the variable in which we have the fitted regression model, that is album sales.3. so these are, this is beta 1, beta 2 and beta 3, and these are the standardized betas. Okay, how we are going to interpret? As I told you that first of all you must calculate the standard deviation values in order to understand the interpretation of this one. So let's interpret it. So what does this particular value mean is the if the advertisement budget expenditure increased by one standard deviation. So one standard deviation means what? That means we are going to calculate the standard deviation of the advertisement expenditure, and that is this one. So this is one standard deviation, that means equal to this one. So that, which means if I'm going to increase the investment in the advertisement budget is this amount, that is the one standard deviation of the advertisement budget, the album sales will be increased one standard deviation. Okay, so one standard deviation means right now the value of the beta is basically 0.511, so that means 0.511 standard deviation of the album sales. And what is the album sales? That is this one. So 0.55511 multiplied by the standard deviation, this one, that is this one. So in short, we can say that on spending the amount on the advertisement budget is equal to this one, the sales will be increase of the album is this one. Okay. Again, if we are going to make sure the effect of other variables are going to be constant. Okay. So this is true only if the effect of other variables are constant. So I hope you got the idea how we are going to interpret the standardized version of the B values. Okay, now let's find out whether this regression model is accurate or not. So for that, first of all, we need to check, is there any particular data point which may affect this regression model. So for that, we can calculate the standardized residual, Cook distance, leverage value, and covariances. Okay, so let me calculate this one through R first. Okay, uh, this this is, so with the help of this command I am going to calculate the values of standardized residuals. Okay, that is R standard and the name of the variable in which we have the fitted regression model. Okay, I am going to store it in this particular variable. So with the help of this command we have calculated the standardized residual. With the help of this function we have calculated the Cook distance. How we interpret this one we will discuss later. With the help of this one we are able to calculate the hat values, or you can say the leverage value, and the last one we have able to calculate the covariance ratio. And then with the help of this command I'm going to store this data set into the album 2. Okay, that is right. And then I am saying round. Okay, now basically up to 3 digit, that is basically we have stored all the data set in the name of the variable which is album 2, in which we have the actual data set. So we have the actual data set as well as we have the values of standardized residual, Cook distance, hat values, and ratios. Okay, what are the criteria we have studied in when we were talking about the simple linear regression model? Like one of the criteria, if the standardized residual are greater than 2, try to find out those points. So how we can do that? So we are saying that album 2 standardized residual greater than 2, or standardized residual is less than -2. So if I run this one, so I can find out wherever you are finding the value true, which means that data point is either greater than 2 or less than -2. If it is false, that means it is lying between -2 to plus 2. Now, in order to find out, like we are going to store this data set, again, this entire command in a variable called album2 large dot residuals. Okay, so I'm going to run this command by storing the result in this variable in order to sum, like how many variables are basically out of this range. So there are 12 values that are out of this particular range. And then now what I am going to do is I am going to you can say call the data from the album 2. The album 2 those are having the large residuals, mean only those data points should be shown to me which having the large residual. So which one? Which having the standardized residuals are either greater than 2 or less than -2. So I want to see sales variable, airplay, attractiveness, advertisement, as well as the standardized residual. So let me run this command. So with the help of, we can see that all the 12 data points. So data point number 1, 2, 10, these are having the standardized residual either greater than 2 or less than -2.2. Now, what we need to do is we want to calculate the Cook distance, leverage value, and covariance ratio. We have already calculated this one, so we only want to see against these 12 data points the values of Cook distance, leverage value, and covariance ratio. So how we can do that? Album 2 and then the name of the variable in which we have the largest standardized residuals, mean all the data points which having the standardized residual greater than 2 or the less than 2, and then we are saying that we want to see against those data points Cook distance, Lagrange value, and covariance ratio. So let me run this one. So these are the Cook distance. So let me interpret this way. Okay, so first of all, we have seen that these 12 data points having the standardized residual either greater than 2 or less than minus 2. So we have calculated the Cook distance, Lagrange value, and the covariance ratio. What's the interpretation? If any of the data points Cook distance is greater than 1, then we can say that that particular case may influence our regression model, because none of the data points having the Cook distance is more than 1. Okay, then we can say that there is no need to delete any data point from the data set. Similarly, in order to interpret the Lagrange value, because it is also giving us the same kind of information. So what's the interpretation of the Lagrange value? That is basically the average Lagrange value we have to calculate. So how we can do that? That is k plus 1, where k is the number of independent variables. So in our case, that was 3. Okay, so these are the 3 independent variables plus 1. So 4 divided by n is the total number of observations. So we have the 200. So 4 divided by 2, this is basically the average Lagrange value. Okay, then the criteria is we have to calculate the twice, and this is the twice, mean multiply by 2, as well as thrice and 3 times. So multiply by 3, that is this one. If the Lagrange value is lying within, you can say, this range, okay, then we can say that there is no need to delete any particular case. As you can see that all the cases within the boundary of the 3 times of the average, which means all the values are less than 0.06. Okay, only the case 1 is basically closer to the 2 times. Okay, so we can say that there is no need to delete any particular case, or either you can use the covariance ratio interpretation. Okay, so for that we need to calculate the upper limit, we need to calculate the lower limit with the help of these formulas. If the covariance ratio is lying within this range, okay, we will say there is no need to delete any particular data point. If it is crossing, then we can think on that one. Okay, but remember that for deleting a particular case, in that case you can only check the Cook distance, because none of the case having the Cook distance is greater than 1. So we can say that there is no need to delete any particular case or the data frame. Okay, now we need to check whether the errors which are we are getting after fitting this regression model are independent or not. So for that, this assumption can be checked with the help of Durbin-Watson test, in which h naught, the row, is equal to 0 and alternative is row is not equal to 0, which means there is a first order autocorrelation, whereas alternative is there is no first order autocorrelation, there is a first order autocorrelation. So how we can do that? We can do that with the help of this command. So I will run it. Okay, the rule of thumb is if the Durbin-Watson test value is lying within this range, then we will say it's a normal. Okay, but if it is greater than 2.5 or less than 1.5, then there is a case to concern about it. Like even field 2019 says not only 1.5, if it is less than 1 or greater than 3, then there is a case of concern. So let me run the Durbin-Watson test in R. So for that we need a package called car. Okay, and we can run, either you can use this particular function, okay, or either you can use the second one, DWT. So both are fine. So in both the cases we can see that the Durbin-Watson test values are lying within the range of 1 to 3. So that means there is no need to delete, or that you can say errors are independent. So the next thing we need to check is the multicollinearity, whether there is a multicollinearity in the data set or not. So how we can do that? That is with the help of variance inflation factor, and how you can calculate that is this one. So normally the main idea is they are saying if the variance inflation factor is greater than 10, then there is a multicollinearity existing. If the variance inflation factor is less than 10, there is no multicollinearity in the data set. Okay, so I have calculated the variance inflation factor with the help of this particular function. I will also run in R and show you. As you can see that advertisement budget, airplay and attractiveness. Against all that, we have variance inflation factor less than 10. That means there is no multicollinearity exists. Okay, or you can say if there is one, that means there is no correlation. So there are multiple type of interpretations are available, like the average variance inflation factor greater than 1, the regression is biased. Okay, if the average, so that is basically we can calculate that one. Okay, but normally people are mostly using this particular interpretation, that if the variance inflation factor is greater than 10, then there is a cause of concern, but if it is less than 10, then there is no need to worry. Okay, similarly, we can also find out the tolerance, that is basically 1 over VIF. Okay, so that is basically zero point 0.1, or we can say that is if the tolerance limit is greater than zero point 0.2, then there is a problem. Okay, so in our data set, there is no multicollinearity exists within our data set, as we can see that even through R, when I am running this VIF function, so the values are, all the values are less than 10. Now let's calculate the VIF through in R. So how we can do that? That is with the help of this function. So if I run this one, so as you can see that all the VIF are less than 10. So that means there is no multicollinearity exist in our data set. Okay. Now, in order to check the other assumptions such as the normality in the data as well as the homogeneity in the errors, so we can use this plot function, and if I enter, we can get the plot of residual versus fitted. We will get the plot of normal QQ plot and scale location plot. Okay, so with the help of this one, how we can interpret whether there is uh, we can say that as you can see that because there is no trend between the residuals as well as the fitted value, so we can say that there is no heterogeneity in the variance. So that means the variance between the residual and the fitted values are constant against every data points. Similarly, the data seems to be normal, mean the residuals are data seems to be normal. Similarly, the scale location, because the difference between the residual versus fitted and the standardized, or you can say scale location, is in the residual versus fitted, we are using the residuals of the residuals as well as the fitted value, whereas in scale location we use standardized residuals versus the fitted. So these two graphs are giving us the same kind of information, because that the variation against every fitted value, the standardized residual, the variation the standardized residual is almost same, or you can say constant against every fitted value. So we can say that there is a homogeneity. So if there is a particular trend, then we will say there is a heterogeneity exist, or you can say the variances are not constant, because right now the variances against every fitted value is almost same, mean the variation is almost same, then we can say that there is only a homogeneity exists. I hope you got the idea how we can perform the multiple linear regression model in R, as well as how we can interpret those results, as well as how we can check their properties. So thank you so much. See you in the next video.